Like before, like we did for simple random sampling, it is now very important, of course, to discuss the analysis of systematic samples. And while there can be actually an important, even a huge benefit to using systematic sampling, it's not always easy to really reflect that into the calculations we do later. I'll try to make that clear as we go. So, for example, for the estimators, it's easy. They're identical. Simple random sampling, you calculate the total, or you estimate the total in the same way as with systematic sampling. The same also for average proportion. Nothing is different. For the variances, again, there is some confusion about the conditional and the marginal view. If you take a marginal view, you say, hey, you must take the variance over all possible samples from all possible lists. So that is indeed a different story. If you say no, 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 and that's the view that I would prefer, we need to make sure that we do capitalize, that we do make use of what we've actually brought forward. That is the use of that list. We think that's a good list. So what's the point in using a list which we consider a good list, if then later we have to average over good and bad lists? No, that's not the idea. So some people actually use the same formulas like Scheffer, Mendenhall, and Ott, which means they take a marginal view. Some authors consider corrections like these people, and especially Notnerus in his book gives a very lucid, very clear treatment of systematic sampling. But some of these corrections are awkward to do in practice, although software tools make it a little easier. A way to think about it is a list is actually creating a cluster. So if you consider all possible lists so that all samples are spread over all the lists, which means every list, it's basically like a bunch of grapes. One bunch of grapes is different from another bunch of grapes, and so a bunch of grapes is a list, and all the grapes are samples I can take. A grape is in one list and not in another one. So we may say that grapes becoming to the same vine actually are clustered. So in the same way, all of the samples belonging to the same list, coming from the same list, is a cluster. And of course, that's not a real, genuine cluster that we observe in the population. No, it's synthetic. We create it as researchers, but there may well be a certain amount of correlation in such clusters. So let's define, and that's very important, the within cluster correlation. So within cluster correlation, why do I say it should typically be negative? Well, what we do is, in systematic sampling, we start with large towns, medium-sized towns, small towns. The town sizes are negatively correlated, because if we look at a few large ones, we know, and there must be small ones. Whereas if we cluster, we would take all towns from the same stratum, which is maybe big towns, and they would be similar. But here they are dissimilar, negative correlation. And by the way, before you start panicking over negative correlation, that's a good thing in this context. Because if we look at the population variance, let's just start there. The population variance under systematic sampling is the same quantity as under simple random sampling, so let's leave it at that. We just take it over. But then there is a correction term. And look at that. If that rho would be 0, the correction term vanishes. If rho is negative, the correction term is less than 1, so we have a smaller population variance. And then, of course, it carries forward in where I'm using that quantity. And for a proportion, the same. There is the typical intra-class correlation correction. Smaller variance is better. So how can I get a smaller variance? Well, by negative correlation, of course. Okay, so the intra-cluster correlation. Let's look at that in a few ways, using ANOVA sums of squares, using hierarchical models. That's the way to look at it. So let's do that. And let's say we are going to introduce double indices, not single, but double indices. So we have subject J, sample take, person, household, whatever, unit J, in cluster I, cluster being sample in this case. Mu is the overall mean, the population average. Mu plus BI is the cluster-specific average. So that's what you estimate if you take a specific sample and don't know the entire population. And it's fair to say there is a certain distribution on that, right? The mu plus BI, so therefore the BIs, they vary. From one sample to the other, I don't get the same mean, I don't estimate the mean in the same way, so there is some variability. But likewise, even in a given sample, not every unit is the same. There is unit-to-unit variation, and that's the epsilon. You would call it the measurement or residual errors in some cases. Okay. Terminology used in mixed models is mu is a fixed effect, B is a random effect, and epsilon is a residual error. So, this is a linear mixed model. And you can say, okay, the variance of Yij is, of course, the sum of the variances, if they're independent, of every random term. So the variance of B and the variance of epsilon. Covariance, that is, what is the relationship between two units, different units, but from the same sample? Well, they do not share their epsilon. They have a different epsilons. They share their B, and the B and the epsilon is assumed to be independent. So brief, the only thing that remains is the variance of B. So, from a variance and the covariance, we can derive the correlation, and this is called the intra-cluster or the intra-sample correlation. Tau squared divided by lambda squared plus tau squared. So you can say this is basically the model we're considering. There is the overall mean, there is a variance, and that's made up of the variance around the average of the cluster, and then the way the clusters or samples vary around the population as a whole. We call that compound symmetry. We can fit such a model in SAS, so let's do that. Let's try and do that for Surveytown. For list X, remember, the number of lots, and Z, the number of newspapers. Okay, so let's print things first, and then we see the data. List X, 8 observations. They belong to, with this list, 1 and 2 is sample 1, 3 and 4 is sample 2, etc. 5 and 6 is sample 3, and they correspond to units 1 and 5, 2 and 6, 3 and 7, 4 and 8, because that's the way you cycle through the list. 1 and 5, 2 and 6, so you see 1 and 5, let me start again here, 1 and 5, 2 and 6, 3 and 7, 4 and 8. Here it's 1, 6, 2, 7, 3, 8, 4, 5. And indeed, each one, there is an overall mean, and we know what the overall mean is, or the overall total, that's 36. So the mean is 36 divided by 8, 18, 9, 4.5. But the cluster-specific means are 1 plus 5 divided by 2, that's 3, 4, 5, and 6. And here, 7, so that gives 3.5, 9, that gives 4.5, 11, that gives 5.5, and then 9, that gives 4.5 again. So the way these averages that I wrote vary around the overall average, 4.5, that's the B's. But then individuals, 1 and 2 here, number 1 and 5, they vary around their average 3, that's the epsilons. Okay, so let's fit this model and say there is a compound symmetry structure playing. Y is an overall average, that's what we are doing here. And the class statement is to define sample, because we do this with sample as the unit. The repeated statement specifies the variance-covariance structure and says all units belonging to the same cluster are potentially correlated with a correlation structure that we chose to be compound symmetry. Now, if we do that, we see that the correlation is negative. And we shouldn't be surprised about that, because we said if the list is well chosen, A small value is compensated with a large value. So that is, they're not similar, they're dissimilar, negative correlation. And it's quite a bit, minus 0.52 for list X. Okay, now, that is this value rho. Huh? If you would be sampling with simple random sampling, you would think there is no correlation. Okay, we'll see what that gives. So the fixed effects are the estimate 4.5, that's fine. That's the overall average, that's what we would expect. And now the correlation matrix, indeed, if we do the same thing with simple random sampling, we can do the same and see what samples would come out with simple random sampling. There are more. If there are 8 units, there are 28 samples of size 2, and there the correlation is minus 0.14. But hey, we would have expected 0. The thing is, no. If you sample without replacement, there is some dissimilarity, because no 2 units are identical, which means they're a little different. Different means negative correlation. If you sample with replacement, the next unit really is independent of the previous unit because it can occur again. But without replacement, if it occurs, it's put on the side and it cannot occur again. So there must be a difference between the current and the next unit. It's not a lot, but there is a small negative correlation. And that explains what we have seen before, that sampling with replacement, where the correlation truly is 0, is less efficient than sampling without replacement, where we have a small negative correlation benefit, because that's the way to think about it. Okay, for list Z, the correlation is hugely negative, minus 0.8, so that gives a very large correction. So if you rewrite these relationships a little bit, you say the variance, or a way to look at it is the variances divided by the correction factor is a constant. So if the correction factor is smaller, the variance is going to be larger. If the correction factor is large, so it compensates. On the first list, this is, for example, what we have seen before. On the first list, the second list, we see the 5.52, 80, 14, all negative. So you see this, the larger the negative correlation, the smaller the corresponding variance. It's proportional to it. Okay. For the artificial population, if we do the same, simple random sampling without, correlation is minus 0.33. Smaller population, so that means it leads to a stronger correction. With, it's always 0. List 1, minus 60. List 2, which was a bad choice, because that's a positive correlation. That's not good. Your units are too similar. That's not good. List 3, there the correlation is perfectly negative, minus 1, and then the relationship is even undetermined because it's 0 be divided by 0. So the base variance of 6.2 is corrected downward, and once it's corrected upward, it balloons in the air because we have a bad list at that stage. Okay, so the more heterogeneous the samples are, the more I make them heterogeneous by systematic sampling. And by the way, think about that. By stratification, when the stratification chapter comes, the better it will be because the more the variance will go down. And then sample size calculation, what about that? Well, think of an average. The variance of the average is the portion that you would get with simple random sampling multiplied by a correction factor. And that correction factor takes the design into account. Not that we made a mistake in simple random sampling. No, now we need a correction factor. And now we can solve that for n. You see you have a quadratic equation, but you can solve it and choose the appropriate route. Straightforward to solve, and then you have your sample size. There's only one problem. You need to have an idea of that correlation. And that's easier said than done if you want to do sample size calculations. So you need to do a guess. So that's why some people say, okay, let's assume it's not there. Is that sensible? No, in very small populations, no. But in larger populations, the negative correlation really cannot be very terribly negative, and therefore not really correcting for it. And in other words, doing the sample size calculation as if it were simple random sampling would be sensible. But in small populations, no, it's actually hurting a little bit. You're spending too much sample size. So, for sampling without replacement, for the average, for the total, for the proportion in absolute terms, for the proportion in relative terms, these are the equations that you need to solve. And yeah, we can write down the roots explicitly, but they look ugly, of course. With replacement, or when the n goes to infinity, it's a little easier, and then you see that you do get corrections that depend on the row. 1 minus rho, but also rho here. So here you see the corrections indeed. So let's illustrate. Let's illustrate how this works for a given problem. So the example of sample size calculation, P is 0.6, Q is 0.4. We request a precision of 0.05 square, so the expression for large samples becomes what I've circled here. So solving the quadratic for various values of rho, going from -1 to +1, you see what happens. With or without replacement is a little different, but for negative correlations, well, you see that with replacement and without the quadratic is the same. But then, if you go negative, you see it doesn't change all that much. And then all of a sudden, when you go to positive correlations, you see that it doesn't make sense anymore. But also, you see that without replacement, you get huge sample sizes. So if the correlation is negative, if your list is well chosen, you can really reduce the sample size from 95 to 50 or 30, and that's where this is actually where it's realistic. But if you would have a positive correlation, that means your list increases the similarity, like every time the corner house, every time the train coming from Brussels and not from anywhere else, you make your units in your list so remarkably similar that you're really hurting yourself. So your list must be related to the listing variable must be related to the survey variable and listed monotonically rather than the other way around. Okay, and that brings me to the end of this part. The end of the chapter number 10, but also to the end of the part, and next time we will deal with benchmark estimation.